Okay, so the next thing that we wanted to discuss are large waves. So some of these are just large gravity waves, like what we've been talking about, but we're really interested in large waves that have other characteristics, things that relate to the rotation of the planet, maybe even the rate of change of rotation of the planet, the way that the gyres cared which direction north was. So too will some of these waves sense that. You might wonder how such large waves would get forced. Well, one of the obvious ways is that they're forced by the tides, because the whole planet on a planetary scale experiences the tides. The waves that are going to be most excited by that tidal forcing are the waves that are of the right frequency and the right size to match up with that tidal forcing. Okay, so today we've covered fast, that is surface gravity, internal gravity waves, and deep and shallow water. We're now going to consider larger, slower waves. They come from astronomical forcing, so we need to get a handle on how diurnal, tidal, seasonal, orbital forcing works, what Rossby and planetary waves are, what Kelvin waves are. So periodic force in the ocean. So wind force in the ocean has a mean and a stochastic component, but there's also periodic forcing, because perturbations to the solar, diurnal, seasonal, orbital, and perturbations to gravity, tides are present. So there's a diurnal cycle in solar heating. There's a diurnal cycle in solar and winds for that same reason. There's a diurnal seasonal cycle in solar heating. There's a seasonal cycle in winds, etc. Are there any waves that respond to that? Well, we're thinking of things that have very low frequency now. So they're going to have very long wavelength for the same phase speed, or maybe they just have a different phase speed relationship. Remember, the phase speed is the ratio of frequency to wave number. The group velocity is the derivative of frequency with respect to wave number. For non-dispersive waves, these two are equal. For dispersive waves, they're unequal. So here are some of the dispersion relations that we've talked about so far. We've got one that's for the non-dispersive plane waves. And a particular example of that are long surface waves or shallow water waves, where GH is the phase speed itself. Square root of GH is the phase speed. And short surface waves, deep water waves, they go, remember that tangent goes the other direction, so we get omega squared equals GK. The surface waves for both short and long, or deep and shallow water, gives us this tangent factor, that tangent of KH factor. Tides. So here is Mont Saint-Michel in France, which is a famous place to go and check out the tides, because the road is only open when low tide. You basically take a bus in, you get locked up until the tide comes in and then goes back out, and then you leave. So all visits there are 12 hours long. It's kind of interesting. We're close to it. Obviously that offers some protection, but it's also just a beautiful place. And then a tidal bore. So this is in the Chengtang River, which is when the tide rushes into relatively shallow water, and that tidal wave, the crest of the tide, actually starts breaking, and it makes a big bore. This is a relatively rare phenomenon. You really need just the right size and shape of river. There's a pretty pronounced one in the Androscoggin River in Maine. It's probably the closest local example. So tides are the response to astronomical forcing, mostly due to the rotation of the Earth and the revolution of the Earth and Moon. There are two ways to think about tides. One is the equilibrium theory, which is not actually a wave theory at all. It's just, suppose we think about gravity being stronger on some parts of the Earth than other parts of the Earth. How does the water rush into those places with excess gravitational attraction to the sun or moon? That's called the equilibrium theory of tides. But the dynamic theory of tides is needed if you want to predict why some places have much bigger tides than other places. And that's really a wave resonance phenomenon. So the key ideas in the equilibrium theory of tides are that there are two bulges, one near and one far. There's solar and lunar effects, and then there's something called spring and neap tides, which is when the solar and lunar effects are either in constructive, that's the spring cycle, or destructive interference, that's the neap cycle. So you can get all fancy about this, and like Wunsch likes to, talking about the zenith angle and the medians and whatever. There's a whole lot of geometry in tides. Think of it in maybe a simpler way. We have a direction of attraction between our planet and the sun. So the gravity is on the axis between them. As you go around, you get the motion due to gravity, and then there's the inertia, and then there is the acceleration you need to keep staying on your elliptical orbit. So if you are on this side of the planet, the close side of the planet, you're actually experiencing just a little bit more gravity from the sun. And if you're on the far side, you're experiencing just a little bit less gravity. So if you're on the near side, you're being yanked away from the planet toward the sun. And if you're on the far side, the planet is being yanked out from underneath you. So there are two bulges in the equilibrium solar tide. One on the close side, since the gravity is stronger there. One on the far side, since the moon yanks the Earth away underneath. The moon's gravity is sufficient for the solid Earth's centripetal acceleration. Sorry, this is talking, but not so on the far side. So centripetal acceleration, that's a little bit funny, but that's sort of trying to get at this inertial effect. It's essentially the centrifugal force, but in the plane not rotating with the frame of reference, not rotating with the planet. So we have this near side bulge, and it doesn't matter whether it's the moon or the sun, it's true in both cases. The difference between the moon and the sun is, of course, which direction the tide is pointing, and also that the period is a little different because the solar day and the lunar day are a little different because the moon is actually moving pretty substantially each solar day. So you get a little bit of a different timing between those two. So slightly different frequencies between the lunar day and the solar day. And so the lunar tide and the solar tide have slightly different frequencies. So the bulge toward the moon is on the near side because the gravity is stronger here. It's being attracted more. The water bulges upward. The bulge on the back side is because the planet is being attracted more so than this water. So the planet is being yanked out from underneath of that bulge on the back. So what you would imagine is that the water would just flow in this kind of a pattern toward that moon, and as the Earth rotated, that they would just keep moving, the water would just keep moving to have this kind of a bulging pattern. This is obviously exaggerated. The real tide is only about 20 centimeters in open water, so you wouldn't be able to see it, the deformation. The sun and the moon don't coincide because there are 3 different days to keep in mind. There is the sidereal day, which is how long it takes for the Earth to rotate. That is what we really should be using for the denominator when we calculate F or when we calculate omega. That's really our rotation rate of the Earth. The solar day is from noon to noon. It's when the sun is at the highest point in the sky to the next day when it's at the highest point in the sky. Because the Earth is moving relative to the sun, the sidereal day and the solar day are not the same. They're just a little bit different. A sidereal day is 23 hours, 56 minutes, 4 seconds. Solar day is 24 hours. That's the one we set our clocks by. A lunar day is a little bit longer because as we go around, the moon has also moved relative to the Earth. And so it takes us just a little bit longer to catch up with it. So the Earth's rotation on itself is the fastest because the Earth is going around the sun. It takes about 4 minutes longer for it to get back to noon, and it takes about 50 minutes longer for it to get to have the moon in the sky at the same point because the moon has moved appreciably each day farther in its orbit around the Earth. So we have this little movie which shows you some of the pieces. So now you can see there's in yellow, the solar bulge, and then in purple, the lunar tides. And so we start with a spring tide. Now we have a neap tide where they're constructive. Spring tide, neap tide, spring tide. So spring tide happens at what phases of the moon. When the moon is on that side, this is a new moon. When we have a half moon, we get a neap tide. When we have a full moon, we get a spring tide, neap tide, new moon. So the phases of the moon, the equilibrium tides, the big tides are the spring tides where the bulges are adding together. The smaller tides are the neap tides where they're not adding together. And that's what we tend to get. And so the spring neap cycle varies with the lunar and solar alignment and your location. In some places, this is 2 different locations in New Zealand. Some places really don't show much variation with spring and neap at all, whereas other places have huge variations between spring and neap. Why is that, you might ask? Well, it's because of the wave theory of tides. The equilibrium theory of tides would not predict this kind of regional deviation, but the wave theory of tides will, the dynamic theory of tides. There's going to be waves that resonate in some places and not in other places. And so that's going to give us a big distinction between springs and neaps. This is a map of the world showing the places where the semi-diurnal tide, that's twice per day, typically lunar tide, or diurnal tide once per day, typically lunar tide, or mixed tides are. And you can see it's not an obvious pattern why that would be. All different kinds of tides, all different kinds of places. Yep. So the tidal forcing is a global signal. The whole Earth is experiencing some fraction of this tide, but the tidal response is local, which depends on the bottom depth, the shape of the continents, is particularly in the dynamic theory. So the tidal response is really a forced wave. So the dynamical tidal response is a forced wave, one whose frequency matches that of the forcing, but the amplitude, the wavelength, all of that is a function of the local parameters, the local basin dimension, the local depth, all those kind of things. So the spatial pattern of tides in the open ocean, there's this concept of an amphidromic point. So this is a map of the amplitudes of the tides, and then these funny little spidery patterns underneath are the amphidromic points. So the tides are going around and around these little points in along these phase lines. So, and as the tide increases, you're going around and around each of these amphidromic points. An amphidromic point is a no tide point. It's like the antinode of that reflecting wave in the basin that we talked about last time, except now it's not reflecting, it's propagating around in these larger basins. Here's just a zoom in on some of these amphidromic points. You can see that they're relatively complex. The Hawaiian Islands, they're in between the islands. The propagation of these is an extremely complex wave topography tide interaction problem. Relatively hard to predict. Not so hard that we can't do it with computers, but hard to predict intuitively where these points would be. And of course, tide patterns affect biology. This is actually a photo from the town that I grew up in. I grew up in a tidal marsh town, West Point, Virginia. And so everything there was about the depth, the currents, the salinity, the temperature. Narragansett Bay is the same way. Most of the currents in the bay are driven by tides, most of the mixing in the bay, the location of the salinity in the bay, the freshwater in the bay is all driven by tidal mixing. Tides are really repetitive, so they're easy to accurately predict, just empirically, just saying, I'm going to fit something to the sidereal day, the solar day, the lunar day, the twice sidereal, twice lunar, fortnightly, etc. You can do pretty well with that. You can actually even anticipate some of the dynamical aspects if you're doing it, making that empirical prediction at each location, like every tide gauge, say, you can do quite well with that. But dynamical computer models are pretty accurate. They're becoming really accurate, becoming better actually than the purely empirical fit. The advantage of dynamical computer models is you can put together the tides with changes in the currents, changes in the winds, changes in storm surge, and get an even better prediction of what's coming. More details there. So here's some observations, here's some predictions of the tides, and you can see that this incoherent part of the tide is has to do with other things like changes in the winds, changes in the storm surge, and that kind of thing. All right. In addition to changes to the gravity of the moon and sun, rotation of the Earth leads to thermal forcing variability from the diurnal cycle, seasonal cycle. The diurnal cycle results from the Earth's rotation. Seasonal cycle results from the Earth's orbit. And so we expect thermal forcing to set off things like we've talked about the mixed layer depth changing over the seasons. There's also a diurnal cycle in wind stress, surface heat flux, temperature profiles, and the ocean respond to that. And so you might actually set off some kind of wave if you had a wave that was slow enough to respond to the seasonal cycle. Here's the standard deviation of 9 to 15 month variability in ocean heat fluxes. So this is air sea heat fluxes, basically a map of where the variability is in the annual fluxes. So the top is in shortwave. This is the sun changing. This is the part we're always thinking about, but actually the long wave, the outgoing radiation also changes. Oh, so this is a long wave down, a long wave up. They're also changing because the response of the ocean temperatures and the atmospheric temperatures is not exactly in phase with the solar temperature. Sensible evaporation, precip, or latent heat fluxes are also rather different in comparison to these incoming solar. This is a very complicated pattern of variability on the seasonal cycles. When we watch these movies, so what it looks like, sorry, I can't play them all at once. You can see that in radiation, there's a lot of variability in relatively complex patterns. You can see things like differences between land and sea, differences between the Ekman upwelling regions and other regions in the ocean. The cloud fraction is also changing. So not only is the shortwave changing because of the incoming solar, but the clouds are changing along with the seasonal cycle as well, complicating how much of the sun actually makes it to the surface. And so the sea surface temperature that responds to that is relatively complex. It depends on the radiation, it depends on the clouds, depends on the sea surface temperature and how much is radiated out. And it depends, of course, on the currents and mixing, the side that we're thinking about when we think about oceanography. The land process also involves things like spring greening, all those kind of things. The water vapor depends on the wind speed, the air sea temperature difference, the precipitation. There's a lot going on when we think about a seasonal cycle. Interestingly, though, I think a lot of people study El Nino and these other oscillations on the large scale that are hard to predict and much more complicated than the seasonal cycle. The seasonal cycle has a lot of impacts, but we certainly know what the drivers are. And in fact, we also know that it comes every single year. When we look at climate models, they do a pretty bad job on the seasonal cycle. They also do a bad job on El Nino, but in some sense, the seasonal cycle is maybe an easier target to study. On longer timescales, like Milankovitch timescales, we know that the eccentricity, the tilts, the precession of the Earth changes, and we can think about very long timescale changes and the response of the climate system to those. These are really different because they're so long, tens of thousands of years long, that it's the equilibrium response, as in analogy to the tidal forcing, is the only thing we have to worry about. There's no dynamical response really on these timescales of the oceans. There might be of the ice sheets. Once again, lots of complicated geometry to do with the solar cycle. Not something we want to dwell on too much, but there's a lot of discussion of it in Wunsch. And so a climate model resolves this part of the story. In there are the tides, conceivably, the Kelvin waves, the baroclinic Rossby waves. We could be doing this better than we are, and that's part of the game. Okay, so what's a Kelvin wave? So we talked about plane waves, plane gravity waves. We talked about them even a little bit about inertia gravity waves where the effect of the Coriolis force is on. And then we watched a few movies which had these peculiar propagation in one direction or the other in the rotating coordinate system. So a Kelvin wave is that kind of a wave. So instead of a plane wave where u and v in height are oscillating everywhere, Kelvin waves require some kind of boundary. The boundary could be a coastline, and it actually could be the equator. There are two different things, two different ways of getting at that. So if we take our shallow water equations that we talked about before, you know, we have the momentum equation, we have the thickness equation. We can solve it in a model. We get something like this, and this is in an F plane, so you can see that the arrows aren't just parallel to the crest and troughs, but they're actually rotating around. It's a little hard to see because they're not very big arrows, but there's a little bit of Coriolis force there. In the Kelvin wave, if we have this boundary where u equals 0, we get a different class of solution, and we set u equals 0 not just at the boundary, but everywhere. Then we have only a v velocity to mess with. If you go through the process of taking these two equations, set u equal to 0 everywhere, linearize the ddt's into a partial derivative with respect to time, and then find an equation for v, the other velocity, you find this kind of an equation. Hey, it looks like a wave equation, second derivative in time, second derivative in y, some kind of speed. That speed turns out to be the same as the gravity wave speed. Cool. Is this a gravity wave? Kind of. But we have a Coriolis force, and we have this additional weird u equals 0 force. U equals 0, not force, but assumption in the beginning. So how does it work if we continue? Is it following beyond the gravity wave? It turns out that they're going to be, it has a structure in y and a structure in x separately. So the structure in y looks like a unidirectional propagating wave. It's just some function of y plus ct. So even though this looks like a two-direction gravity wave, this, when we're getting more careful regarding after we've thrown away a spurious solution, we find that there's only one direction the Kelvin wave can propagate, which is towards minus y in time in this case. And then there is this exponential decay in the x direction with a mystery factor called r, which is the Rossby deformation radius. And so u is 0 everywhere, but v is definitely not, and neither is eta. So there's this funny exponential decay in the x direction and non-dispersive propagation in the y direction. Really interesting. So in time, this kind of wave propagates toward negative y, that is, with the coast on the right in the northern hemisphere. In the southern hemisphere, you get the coast on the left. So here's the Rossby deformation radius, square root of gh over f, which is just a combination of parameters. But if you take my GFD class, we'll spend an awful lot of time talking about the significance of this particular length scale. It's kind of a length scale that's convenient, that's built out of the parameters in this kind of a problem. In the ocean, for the external one, this is about 10,000 kilometers. For the internal one, that is with a based on just motion above the picnic line, this is around 50 kilometers or so. So for barotropic Kelvin waves, we expect them to fill the whole basin. for baroclinic Kelvin waves, you expect them to really be detected just along the coastlines. So this flow is geostrophic in one direction, d eta dx. D eta dx is actually equal to v, cool. But it is not geostrophic in the other direction. It's like a gravity wave in the other direction. So d eta dy is a gravity wave. D eta dx is geostrophic balance. So funny, blended geostrophic gravity wave balance. So here's what it looks like as it propagates along the coastline. So here we have the coast on the left. So you have an acceleration of the phase. In the center of the phase feed, there is a divergence to one side, and there's a convergence on the other side. And so you're piling up fluid when the convergence ahead of the flow, and you're diverging and pulling away fluid and sinking back that sea surface height anomaly behind it on the other side. In the opposite sense, when you have a sea surface low, you get the reversal of the convergence and divergence, but you're still propagating the wave in the same direction. That's the funny part about it. Like this. So we talk about this. Here's the non-rotating channel case. So now that we have a channel, we have u, or in this case, it's the y velocity that's equal to 0 in the Kelvin wave approximation. We can see in the regular old gravity wave case, we don't have that problem at all. We get these nice big circular patterns at first, and then turn more linear as we get farther away down the channel. Here's what happens if you do that same periodic pulsing where the rotation rate is rapid. You see that you're propagating with the wave, with the coastline on the right. It doesn't matter whether you're a high sea surface high or a sea surface low. You're propagating with the coastline on the right. If you could look more closely in these arrows, you would see that pattern of converging and diverging and advance and behind that we just saw in the schematic here. If you put that plunger, that source, right up against the wall, you see that you don't excite really waves on the opposite wall, but you excite positive and negative sea surface anomalies that really hug against the coast. The distance away from the coastline that these waves are decaying is this Rossby deformation radius, which in this case is about 1 meter in this like kind of lab, or 1 times 10 to the 4 meters in this kind of lab, in this sort of scale for this problem that I've chosen. So now we go back to those amphidromic points about the tides, and hey, notice that they're always propagating with the coastline on their right. Coastline on their right. This is the Bay of Fundy. This is just an idealized domain. 1 hour, 2, 4 hour, 6, 8, 12, 10, 0. Propagating around and around like this is a sign that these really are Kelvin waves that are propagating. So the amphidromic point is the point where the Kelvin wave is not touching in the middle, or is being affected equally by all of the wave amplitudes in all directions. You expect the biggest amplitude to be up against the coast. You expect it to be a relatively exponential decay that has to do with the geostrophic balance. And you expect resonance. When this Kelvin wave goes around and around in exactly a tidal period, you would expect it to get bigger and bigger and bigger if it gets kicked the same tide every time it goes around. So that's the explanation for why the tides in the Bay of Fundy are so strong, is because as this Kelvin wave runs around and around, it gets kicked basically once per tidal cycle. Sorry, not the Bay of Fundy. This is showing the amphidromic points in the Gulf of St. Lawrence. Excuse me. Bay of Fundy also has this kind of a pattern, but it's not what's shown in this figure. Here's the Bay of Fundy now, zooming in. You see that there's a resonance because the time for this wave to propagate in and out is just the amount of time that you're getting. It resonates at the same frequency as the lunar tide. Here's an example of Kelvin wave propagation, looking at the tides running around New Zealand. you can see, oh, wait, why is it going the other direction? It's got the coastline on its left. It's because it's in the southern hemisphere. So the geostrophic decay that we talked about flips to the other side when F is negative. Okay, here we're looking at a frequency wave number spectrum of, so here are the frequencies, and up here are Poincare waves or surface gravity waves. Here's the Kelvin wave cutting across. So this is really just a method of plotting the dispersion relation. We're plotting frequency versus wave number. The fact that this and this are separated like this is evidence of there being topological insulation in this system, which is what we talked about a little bit when Brad Marston's been doing research on that. But if you zoom in, there actually is another wave sitting right near the frequency equals 0. So very long time scale limit. That wave is the Rossby wave. And so it has this crazy dispersion relation, which involves both the Rossby deformation radius, the wavelength, the wave number, and the inverse of the X and Y wave numbers, so the magnitude of the wave number is frequency. You can see this is a pretty complicated thing. If this term down here is small in the denominator, you have just minus beta r squared kx, which means that at least in the x direction, it's a non-dispersive wave. In the y direction, it is always a dispersive wave for long or short waves. So how do we think about a Rossby? Well, all right, let's do that same channel, except this time we just do a blob drop. And you see after a while, you get a nice high anticyclone pattern. Cool. And the anticyclone is drifting very, very slowly to the west. North here is to the north, is to the up. And it's drifting slowly, slowly to the west, because this is not just an F plane channel, this is a beta plane channel. So that beta that's in the dispersion relation is non-zero. But it is a Rossby wave is much, much slower than a Kelvin wave. You saw those Kelvin waves run away. This Rossby wave is primarily a geostrophic anomaly, like a sea surface high, a cyclone, or an anticyclone, sea surface high or sea surface low. But then it has a slow drift westward because of the beta effect. So you can go through the math if you would like to do this. Basically, it's assuming that you have geostrophic balance to leading order, and then you collect together all the terms. Notice that these are all linearized equations. You collect together all the terms, and you can find that chug, 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 chug. Replace the UNB with the small terms. You have to figure out which terms in this set of equations are big and which are small. The small terms, you can replace the UNB with the geostrophic UNB. That is with balancing F naught V against this side. You go through that extra step. Now you get something that's starting to look like a wave equation. You have to solve that wave equation for U and V, which is this, and then you find the dispersion relation and where the R is the deformation radius. Don't forget this whole question about reduced gravity that we talked about. So in the shallow water equations, these are all solutions to the shallow water equations. We could have also used the reduced gravity shallow water equations, in which case G is replaced by G prime, which is just the density scaled by it's the G scaled by the density difference between the upper and lower interface, the relative amount. And H is just the thickness of that upper layer. And if you have that, then you can slow down these Rossby waves even more so. And you get this smaller deformation radius, which goes with G prime times H over F naught instead of full G times H over F naught. This one is around 10,000 kilometers in the ocean. This one's around 50 kilometers in the ocean. So this is the more important one for things that fit inside of our basin. If we plot this dispersion relation as a function of Kx, you can see, well, think about what this means. So omega divided by kx is the phase speed. Omega divided by kx, let's see. So omega is positive, then negative. It is negative for positive kx. It is positive for negative kx. So omega divided by kx is always negative. The phase speed of a Rossby wave is always negative. That is westward. The group velocity of a Rossby wave, d omega dk, has to do with the slope of this figure. So it is eastward propagating here where the slope is positive, eastward propagating here where the slope is positive. So for short Rossby waves, they have an eastward propagating group velocity. For long Rossby waves, they have a westward propagating group velocity. So phase velocity of Rossby waves is always westward. Group velocity is westward for long Rossby waves, eastward for short Rossby waves. How fast are these? You can so you can go into thinking about the phase speed for so it's always negative. This is what it's equal to. And at very long waves, you can actually approximate this as just being a non-dispersive wave, which is minus beta naught r squared. So what's the mechanism then of a Rossby wave? If it's these little cyclones and anticyclones next to each other that are drifting slowly to the west, how does it work? Well, imagine we have sea surface highs and sea surface lows like this, which is, or imagine that you displaced a particular latitude of water towards the south or towards the north. And either of those situations, or actually both of those situations, what you tend to have is you tend to have a vorticity anomaly centered around this little black dot. Now think about how this black dot, one of these black dots affects the other one. If you think about, so that's what this little ring with the arrows on it is saying. If you think about a wider ring that includes the other black dot, you would see that one black dot is making the other one move to the west. The other black dot is making the first one move to the west. So these anomalies in vorticity or potential vorticity are a Rossby wave, are what the basis of a Rossby wave. The crests and troughs of a Rossby wave are cyclones and anticyclones, and they advect each other toward the west. You can make it either on a planetary basis where you have a variation in F because of the beta effect, or you can actually make topographic Rossby waves because you have stretching and squeezing in the denominator of the potential vorticity equation. So either F can vary from north to south, or H can vary from offshore to onshore, and you get Rossby waves in both cases. The last kind of wave we want to talk about is the equatorial Kelvin wave. So the equatorial Kelvin wave is like the coastal Kelvin wave, except now we're setting V equals to 0 all along the equator and off the equator. On the northern hemisphere side, the equator is on the right, and on the southern hemisphere side, the equator is on the left. So it looks like we have a Kelvin wave matching up right along the equator as long as that Kelvin wave propagates eastward along the equator. So we put the whole dispersion relation map together. We get surface gravity waves, we get the Kelvin wave, we get the Rossby wave. We actually get this funny other wave called a Yanai wave, which we didn't talk about. This is what we see for equatorially trapped Rossby and Kelvin waves. And we're going to come back to a surprising number of these waves when we talk about how El Nino works. So which go west, which go east, which go both. Remember, over here for K equals negative, everything that's above is going westward in phase. Everything that's below is going eastward in phase. So the Rossby wave is always westward in phase, or for this side. everything over here where K is positive, everything that is negative is going westward, everything that is positive is going eastward. So you've got eastward propagating Kelvin wave on both sides, a westward propagating Rossby wave. And then in terms of group velocity, you have to look at the slope of all these lines and think about how the slope of the lines is positive or negative, gives you eastward and westward propagation. All right. Have Rossby waves ever been observed? Yes, they actually have, or well, something very close to them has. In this groundbreaking paper in 1996, they noticed these sea surface height anomalies that were propagating along, and they were all propagating westward. And they said, great, we have for the first time observed Rossby waves. You could, and if you infer from this, you can try and answer this question based on the dimensions in this problem if you want. The funny thing is that they actually found that these wave speeds were a bit too slow in comparison to what they thought. And so under later study with more satellites where they could distinguish the features a little better and not just have highs and lows propagating westward like this, they actually found that in 2007, that the anticyclones, those, the cyclones and anticyclones that make up the Rossby wave, the cyclones were all propagating with a little bit of northward drift. The anticyclones were propagating with a little bit of southward drift. It turns out that this is a feature of nonlinear vortices or eddies, that they tend to attract themselves to the pole of their same sign. So this little bit of extra drift is an indication that these Rossby waves or eddies are really not behaving like linear Rossby waves. They have characteristics that one would associate more with eddies than with wave crests and troughs. Once you do that and you talk about them as eddies rather than Rossby waves, then there's a nonlinear prediction for their propagation speed. And that gives you the corrected factor that you would, about what you would imagine. What do these guys look like? Well, here's a movie. And you can see that there are lots of little features. Are these waves? Are these eddies? Well, that's exactly the point. This is a movie made from AVISO, which is a multi-satellite sea surface height measurement. I've converted it into kinetic energy and taken the log of it so that you can see all kinds of fascinating waves propagating back and forth. Look how the ones just off the equator are systematically going westward. Hey, maybe those are Rossby waves. The ones right on the equator are systematically going eastward. Hey, maybe those are systematically Kelvin waves. And then off the equator, you can see lots and lots of Rossby wave-like patterns, or maybe they're eddies. Beautiful stuff. So it's not only this steady circulation that we're thinking about when we're thinking about the kinetic energy of the Earth. There's also a superimposed kinetic energy from waves and eddies that really changes the pattern of kinetic energy from something like this to something like this. And in most parts of the world, this time varying energy is actually greatly in excess of the spare drip transport that we've been talking about. So when you go out and measure drifters, you're getting an order of magnitude or more greater kinetic energy when you include the eddy part. And there's a lot of complexity, which Wunsch talks a lot about what the power spectrum is of the eddies and length and time scale, what they look like. Here's another movie just showing some more eddies, zooming around, loop current eddies doing their thing. This is from a high resolution model, which is also in assimilating sea surface height. Unfortunately, Echo, the version of Echo we're using, is not of sufficient resolution to have these eddies really represented. There are certainly Rossby waves in our model, but they're probably not eddies. It's not that high resolution. Hurricane Katrina is one example of something that was strengthened by eddies. In this video, you can actually see that the The dates, these are actually the right dates. They are the right dates. So just as Hurricane Katrina passed over the Gulf of Mexico, it passed over a couple of warm loop current eddies and strengthened. That's when it turned into a Category 5 before coming ashore. It's kind of hard to see in the sea surface temperature here, but there are some eddies underneath. And so here's Hurricane Katrina forming, and it's strengthening zoom right there as it goes over that warm water anomaly from those loop current eddies before it hits New Orleans. So eddies play a role in climate. If we want to forecast climate, we probably need to know the effects of eddies on both the heat transport and the tracer transport, but it also affects air-sea fluxes. This is a big and complicated thing, and it makes everything much harder to model because we presently, because we have to use high-resolution models. We have to deal with the nonlinearities in all the equations. Big mess. So typically, climate models right now, on weather models as well, parameterize the eddies, which is one of the primary things that we do in my group, is try and improve those parameterizations. And then there are a few of these high resolution simulations like the ones I've been showing you movies from. All right, the end. Here's one more eddying solution that's a nice one to look at. Really shows you how alive and vibrant the time varying part of the ocean is. Thank you very much.